the sandwich theorem that we saw earlier with functions also applies to sequences. So if we know that a sequence of numbers, in this case the in-between sequence, b sub n, if we know that's always between a sub n and c sub n, and we know that the limit of a sub n and c sub n are equal to the same thing, then we know that also b sub n has that same limit. That's the sandwich theorem. Now this is going to be really useful when we look at oscillating sequences, because a lot of times we'll see oscillating sequences where we can look at a sequence that's always bigger than that and always less than that, and we can show that they converge by showing that the positive one and the negative one converge to the same limit. A lot of times this happens around 0. It doesn't have to be around 0, though. It could be around some other number also. So this is what the sandwich theorem looks like for sequences. It's essentially the same language as the sandwich theorem for functions, except it's written in the language of sequences instead of functions. So it's pretty familiar to us, or at least it should be. This one's a little different, but it's useful. It says something that might seem a little obvious, but it's not necessarily obvious. So what this says is if the limit of the absolute values of the terms of a sequence go to 0, then the limit of the terms of the sequence also go to 0. We can prove this using the sandwich theorem. So in this case, if we look at just the positive values of a sub n, if we know the limit of the absolute values goes to 0, then we can squeeze this between the positive values of a sub n and the negative values of a sub n, and show that this limit also goes to 0. So you can use the sandwich theorem to prove this. This can be useful also with oscillating sequences that are oscillating above and below the x-axis, and it's a good way to show that a limit approaches 0. So what I'd like to do is look at a few examples here of some limits and whether we can find the limits of the sequences or not.